And here we go. All right. So, I gotta tell you a love story here. All right. So, y'all saw that it was a lot easier to turn the wrench when you. How would you put it? It was easier to turn the wrench and spin the bolt when you were farther away. Okay, give me a little bit more specific language here. The radius, okay, was longer. Someone else other than Jasmine here. What do you mean by the radius?
How far you are from the center? Yeah.
How far you are from the center? So what do you mean by how far you are?
The distance.
The distance.
From
The distance of what? From what to what? Go ahead, Miranda. The distance from the pivot to the point where the force is applied. Okay. So from where I'm applying to the force, or the force to the pivot, that's what we call R. That's like radius. We use that for everything. So that's that distance. So if that R is larger, then I get more turning power. How's that sound? That makes it, that's kind of a bad way of putting it if we're physics, but we haven't talked about power yet. So anyway, you see what I'm getting? It was easier to turn it, right? In engineering, we call that mechanical advantage, all right? In engineering, we call that the rotational force, okay? Because it's sort of like the farther away that I am, then the more of a turn that it gets going on, okay? So we have a word for that, and that word is torque, okay? So, let me tell you before I go and get to details here, I'll tell you a story. So, when I was dating my wife, I had some car trouble, still have the same car actually, but the alternator went out, and so I had to change the alternator. And I am like terrible at all things mechanical, but for whatever reason, I actually had changed an alternator before. It's probably the only thing I've ever done, except maybe the battery. And so I'm like, yeah, I'm gonna need to change the alternator. I'm in the middle of Arlington at a parking lot where I had gone to get a paycheck from one of the jobs I had at the time. And so she comes, so she drives over. She was living in Fort Worth at the time, and so she says, "Oh, okay, well, I can drive you over to AutoZone or whatever." And I'm like, "Thanks." So we go over to AutoZone, get the piece, and I had some tools in the back of my car. So guys, always make sure you have a nice toolbox in the back of your vehicle. Anyway, but for whatever reason, now I'm feeling pretty good about myself because I know exactly what needs to be done. I know how to, and I'm trying to get the bolts off. Okay, but guess what? Those suckers are not moving. Get some WD-40 put on, they're not moving on. I'm there underneath, and I'm like, of course, car trouble, you get kind of frustrated, and I'm like, I cannot get this, and I'm like, I don't know, I have to call, get a tow truck to take this to somebody so they can loosen the bolt or whatever. And my wife, my girlfriend at the time, she's like, oh, well, I've got something that might help. And she goes into her car, and she pulls out a cheater bar. All right, now I don't have one with me, but y'all know what a cheater bar is? It's basically is a pole. She still has it. Okay, it's a metal pole, and it's kind of it's hollow. And what you're able to do is you're able to, and it doesn't. I mean, it's not like, I'm sure you could probably buy one, but you just get a metal pole, or whatever, and you stick it on the end of your wrench or your screwdriver, well, not your screwdriver, but your wrench, and it basically then extends it out, extended it all the way out to here. And I'm like, oh, this is perfect. And so I put it there on the end of the wrench, and I literally went, and the whole thing goes, turn, and came off, and changed the alternator, and I'm like, I'm gonna marry this woman, so she knows what's going on here. She's like, yeah, my dad gave it to me, and I'm like, that's awesome. Anyway, so, fun little story there, and the point I tell you is because obviously with that increased radius, that increased distance, then you're able to get a lot more turning. You're a lot more torque. That's just what we're going to call it. You get a lot more torque. Okay, so what you can think about torque is the rotational equivalent of force. Okay. So we've been talking back and forth last week about how everything rotationally has sort of like its linear, line motion sort of equivalent, or it's parallel. And we had theta and we had omega. So you had like theta in rotational was x, and velocity was angular velocity, and acceleration was alpha. Well, we had force, and when you push something, when you had a push or a pull, okay, then it caused it to move, okay? Well, what do you get something to rotate? Well, it has to be like a rotational force. Does that make sense? And a rotational force is called a torque. And so we use tau, the Greek letter, so to represent the torque. What's that?
There's like a banana that's
Open, sure. Open banana. Yep. So anyway, torque, or force, was equal to mass times acceleration, or better yet, actually, acceleration was equal to force divided by mass. That was Newton's second law. Actually, to be more specific, that was Newton's second law for linear motion. There is Newton's second law for rotational motion, okay? You'll be reading that here, where you're like, okay, I get this. You've got alpha equals torque over mass. But it's not mass. It's rotational mass. Moment of inertia, which we haven't talked about, but we will. So it's I is what we'll deal with that. Okay. So we will we'll hit that up a little bit later. Do y'all have your notes out? All right. Let me see. All right. Make sure you have those notes out. You all have your hand out?
Yes.
Good, good?
Oh, you're not checking it.
I will in a second. Depending on load. I need a string. Okay, so let's look at this together here. So forces with equal strength will have different effects on a swinging door. Allow me to demonstrate what you guys already kind of saw. If my door's open, I can push it right here, and it's not too bad. Kind of give it a little push, and it'll do a little bit of a swing. If I try to do that same push right here, not really rotating as much. Can y'all see that? Break my finger here. If I go even closer to the edge. Anyway, then it gets even harder. Which is actually, by the way, if when we do our lockdown stuff in third period, if you get some like zip ties or a belt and you kind of clamp this part shut, see because it's really close to the, if it's close here to the pivot point, then this is actually a really strong way of holding the door shut. And so, anyway. So yeah, pushing up there, I can push. It's a lot harder here. What sort of rotation would I get if I push out here? Y'all see me? I don't know if you see. I'm pushing this way along the door here. What kind of rotation am I getting? Am I getting? Because I'll hold it in place here. Am I getting any rotation?
No. No.
I'll pull it. Nothing. What's that?
I said you look like you were having a tantrum.
I know. Yeah. You don't, if I'm actually pushing, I guess when I was pushing on the door, that was sort of like force 2 right here. Was that doing anything to make the door rotate?
No.
No, it really wasn't. And if I was pulling, I wasn't either. We've already discussed the relationship between force 1 versus force 4. Which one of those is going to cause more torque?
Force one.
Force 1 will, because it's got a farther distance. Now, look at force 1 and force 3, okay? Which one of those two do you think is going to cause more turning? Force 1 or force 3?
Force one.
Why force 1? You're right, it is force 1. Do I need to have y'all come up here with the...
Force three is just gonna pull it out. It's not actually gonna push it.
Yeah, force 1, okay? It's sort of like all of the force that I'm doing is up, and which is going to be making it turn, okay? Force 3, if you break that force down, some of force 3 is pulling out, okay? And is that doing anything causing it to rotate?
No.
No. In fact, the only part of force 3 that is causing this door to rotate is the y component right here. Force 3 in the y direction. That's the only part that's going to make it rotate. If we had some more time, I'd tie this string here to the end of the wrench, and y'all could try it at different angles, okay? But you'll, and I may still yet do that. But what you find is that the closer this line is to parallel to the door, then the less effective it is. The closer it is to perpendicular, then the more effective it is. Obviously then, if we started rotating it back this way, then we're becoming, once again, less effective, okay? Less torque. So, if we look at this, not a better picture there. Anyway, here's the formula. Torque is equal to the product of the radius, the distance between the two, and F perpendicular, which is the perpendicular part of the force. This is kind of what we saw. If the radius increases, then the torque increases. If the force increases, if you have more force, then you're going to have more turning power, okay, more turning action. So standard units for radius are meters, standard units for force is newtons. So torque is measured in newtons times meters, or Newton meter. It's not newtons per meter, because that would be newtons over meters. It's Newton meter. That's the way that we do it, that we measure it. What can we do for you?
Do you have multimeters?
Yes, they're in those boxes back there. They're the green things. You can just take the small boxes, just make sure the boxes all stay together. Yep, those small ones. You can just stack them. All right, so here's the picture in your book or on your handout. This is the pivot. R is the distance between the pivot and the point of application of the force. F is the force. And then we're going to use this. It's not theta, it's phi, to represent the angle between the force and this line right here, which we're calling the radial line. Okay? So if we were to actually draw, and you can draw this on your paper, it kind of makes it a little bit nicer. This right here, this part, the part of force F, which is perpendicular to the radial line, we call F perpendicular. If we were to imagine this as an X and Y coordinate, we'd call it Fy. This part right here, this component, we call F parallel. So you can kind of use the parallel notation. The F parallel does nothing towards actually rotating this bolt, but F perpendicular does. Now, since this angle right here is phi, we can write a trig ratio. Which trig ratio is going to relate F perpendicular with F? Sine. We would say the sine of phi equals opposite F perpendicular over the hypotenuse, F. So then solve for F perpendicular. F perpendicular equals F sine phi. same picture, just sort of blown up. Another line in the diagram here, and this is on the next slide there, the line that contains the force vector is called the line of action. And sometimes we'll talk about R perpendicular, which is the length of the, it's the component of the radius that is perpendicular to that line of action. And just so happens that you've got, phi right there as well. Anyway, in either case, we've got the torque, which is equal to the radius times F perpendicular, and F perpendicular was the magnitude of the force times the sine of phi. So this is where we get torque equals RF sine phi. Or, sometimes it's just FR sine phi. Go ahead and get out your formula chart. I think you will find that formula there. We'll put a star next to it. R perpendicular F R. Now I think they have, do they have phi or theta on there?
Theta.
Theta? Who cares? An angle is an angle, right? Just make sure that you know the angle that they're talking about. They're talking about the angle between the radius and the force. Okay? That's what they're talking about. That acute angle. So, let's turn the page over. Let's do some problems together. All right. Based on our previous discussion, probably pretty quickly we can give an answer. This says the four forces shown have the same strength, so they're all they're all 10 newtons. Which force would be the most effective in opening the door? Somebody give me a wrong answer. Which?
2. F2.
F2. All right. So, Brooke, why is 2? Why is that not effective?
Because you're pushing against it.
Yeah.
So it doesn't have any rotation.
Okay. Let's just say that F2 happens to be 10 newtons. What's the angle there between?
0.
Yeah, this angle is 0. So, quick calculation. What's the sine of 0? 0. So it's FR sine 0. Well, sine of 0 is 0. So torque here is 0. Does that make sense? Somebody else, give me another wrong answer.
4.
F4? Okay, why is that?
Because it's close to
So the radius.
Yeah, to the radius, yeah.
Okay, yeah. So if this is radius 4, and then from here all the way to here, this is radius 1.
Right.
We would say that radius 1 is greater than radius 4, thus torque 1 is greater than the torque caused by 4. Looks great. Somebody else, give me another wrong answer.
3.
3? Emily, why is 3 wrong?
Because since it has an angle, the perpendicular force would be less.
That's correct. Okay, since it's got an angle, then it's going to be less than the perpendicular, assuming that both of those are the same magnitude, that this is like 10 newtons, and that's 10 newtons. Okay, this is a fun little thing here. So for force 1, it's going to be, let's say this radius happens to be, I don't know, 0.3 meters. So it's force 10 newtons times the radius 0.3 meters times, let's say I forgot the answer and how all this works, times the sine of the angle. Now, what's the angle between force 1 and the door? 90 degrees. Anybody know off the top of their head what the sine of 90 degrees is?
1.
It's 1, yeah. So it's just, it's always be 1, it's the full amount. If you're in pre-cal, you'll remember all the other sines, like sine of 45, sine of 80, sine of all those other things are less than 1. You remember the sine graph?
Mm-hmm.
It always goes between 1 and -1, right? So therefore, this number right here, the biggest it could possibly be is 1. Any other number, it's going to be smaller. It's going to be like 0.8, like 80%, or like 0.7, 70%. So it's going to be a smaller, it's going to be some fractional percentage of those two, if that makes sense to you, mathematically. Anyway, right, so just as a reminder that if it's perpendicular, you don't even really need to write the sine of 90 degrees. That's why in a lot of our problems that we're going to be doing, in which the forces are perpendicular, I'm just going to write torque equals force times radius. Okay? Now that's obviously if it's perpendicular. If F is perpendicular to R. Are you okay with that? I'm just going to write what's torque, and you'll say force times radius. You'll be like, okay. Sometimes, I think when I was taking physics, we'd say force times distance, but that wasn't necessarily really very inaccurate way. Yeah, force 1, most effective. Okay, let's actually do a quick calculation on this. We've got Ryan is trying to open up a stuck door. He pushes it at 0.75 meters from the hinges with a 240 Newton force directed 20 degrees away from being perpendicular to the door. There's a pivot, natural pivot point, and it hinges. What torque does Ryan exert? And then how could he exert more torque? Well, formula, call it out to me. Torque equals
Radius.
times sine of the angle. Now in this case, you better tell me the sine of the angle. You can't just say force times radius because they're not
It
perpendicular.
would be 70 degrees.
Ooh, 70 degrees. Why do you say that?
Because it's 20 degrees away from being perpendicular, so you would take 90 minus 20.
That's correct. We're looking for this angle right here between the force and the radial line. Absolutely. So we've got 0.75 times 240 newtons times the sine of 20 degrees. Now, absolutely, you better be in degree mode on this one. If you're typing in sine, cosine, tangent with degrees, yeah. So torque equals 126 Newton meters. So, is that right? Anybody else have another answer or verify?
Would it be the sine of 20 or the sine of 70?
It's the sine of.
61.56.
Oh, I put sine of 20.
It's sine of, okay.
That's my. I wrote 20 there even after Emily said 70. Sorry, sine of 70.
I got 169.
Yeah, I got 169.
Okay, that's my calculations as well. You did what I wrote down.
Yeah.
Never do what I write down. In fact, don't do what I say either, because I make a lot of verbal mistakes. Just pretty much do the opposite of what I do, and you'll be totally fine. Just kidding. Okay. Boys, I want one of y'all to answer this question for me. How could Ryan exert more torque? Show off his manliness here.
If he was perpendicular.
Okay, say that again.
If he was perpendicular to the pivot.
Okay, so he could push more perpendicularly. Okay, all right. The other guys, what's another way he could exert more torque?
Push it the farthest white space you can get to the end of it.
Okay, so yeah,
Increase the radius.
increase the radius. Got it. That's the second way. And Kevin, push it harder. Right. Okay. There's actually 3 different ways that you could increase the torque. You could increase the torque through the radius or the distance between the pivot point and the applied force by increasing the force, or by trying to make this closer to 90 degrees. Now, if it's already at 90 degrees, then you can't change it anymore. One thing I didn't tell you, all right, but this is sort of like a small point, kind of obvious, but I'm going to tell you anyway. What would happen if you were applying the force right there? Actually, I'm going to make it perpendicular, right on the pivot point. would that cause any torque? Here we go. Observe.
You're not pushing the actual object.
I'm pushing it, but I mean, is there going to be any turning action on this? No, there's not. Okay, why? Can you give me a mathematical reason why?
Because
Mathematical, no.
There's no radius. Because in this case, my radius is 0. You see what I'm saying? The distance from my applied point, okay? So if radius is 0, then that's the reason why. So in the same way, if I push along this, if I push like that, that's an angle of 180 degrees. So if I were to push like this, okay, 180 degrees, what's the sine of 180? Anybody know?
Zero?
0, sine, up, down, right? So it's 0. So if you're pushing along that, right along the radial line, you're going to get 0. We do have positive and negative torque. Just like, remember with forces, if something was pushing in the negative direction, then we said it was a negative force. If something was pushing in the positive direction, then we said it had positive force. Similarly, we have positive and negative torque. Okay? So if it's pushing the object in a counterclockwise direction, then that is positive torque, just sort of like positive rotation. And if it's pushing it in the clockwise, then that's negative torque. Okay? Also, just like forces, we talked about the net force, which was if you added up all the forces, force 1 plus force 2 plus force 3, and so on and so forth. And then we could write that as the summation of the forces. In the same way, we can talk about the torques, the summation of the torques. Let's see, Belle, Miranda, Emily, come on up here. We're going to have a summation of torques example. Ooh, good, natural pivot point. So I'm going to be using this as the natural pivot point. All right, so you 3 ladies are going to apply a different torque on this 2x4. Okay, so Miranda, I'm going to want you maybe push at the end, maybe at a 90-degree angle. Okay. Emily, I'm going to want you to push maybe right here. Okay, a little bit closer, but push at an angle sort of down like this.
Downwards?
Yeah, down like
Okay,
that.
so
Okay, if you
this
can do
is
that. Yeah, sure. And Belle, you come over here and you push in the middle, maybe sort of upwards like that. Okay. All right, are y'all ready? Hands on the. So here's the pivot point right here is where I'm holding it. Okay. All right. Now, what do you think is going to happen? Is it going to start rotating this way? Sort of, from your perspective, what is it? Clockwise? Clockwise or counterclockwise? All right, give it a shot. They're all kind of fighting against each other. Keep going, Miranda. Push harder. Okay, so we're getting a little bit of, do y'all see what's going on?
Mm-hmm.
All right. Now, Belle and Emily, y'all put your hands off there. Now, just Miranda, there you go. See there, she's pushing it there that way. Okay. Belle, your turn. Just on yours. There, kind of push it that way. Emily. So this is sort of each one of them individually. Okay. So you kind of see how much they're each sort of adding. If we were able to have some numbers there, we could figure out exactly what was the torque that Miranda was putting on here, the torque that Belle was putting on here, the torque that Emily was putting on here, and we could actually come up with what we would say a net torque. All right. And it's possible that they could be fighting each other. Okay. Who's most likely to fight between the 3 of you? Miranda and Belle, you're on opposite sides. Sounds good. Okay. So Miranda, I want you to point out there perpendicular there, right? So let's get ready to push. Okay. Now Belle, I want you to push maybe right here in the middle. All right. Ready? Fight. Oh.
Don't get hit in the head, Miranda.
Looks like Miranda's winning. Why is Miranda winning? Do you think?
She's farther away.
Yeah. Now push with that same force, but without Belle being there. You were pushing harder than that, weren't you? Go ahead, push hard, really hard. Push just. I'll make sure it doesn't hit you. Okay. All right, yeah. You were pushing, it was going all the way up like that. So what I want you all to see This is exactly the same. Kevin, head up, please. I'll use this 2x4. Hit the table. What I want you all to see is that rotation works just the same as when two people are pushing or pulling or over the same object. You've got a force of 10 newtons this way and 8 newtons that way. It's the same as if you had a 2 Newton force going this direction. Okay. If you have Miranda with a 10 torque this way and Bell with an 8 torque this way, it's the same as if you had a 2 torque in this direction. Does that make sense? That's kind of what I want you. It's like what I wanted you to see. It's like a vectors. Okay. Have a big seat. Thank you. Before I hit you with the 2x4 accidentally. All right. So go ahead and make a decision on that question there at the table. Which third force on the wheel applied at point P will make the net torque 0? We have a wheel. This is the pivot. You've got somebody pushing it right at the pivot. Somebody else pushing it to the right. Okay? And we have 4 choices, 5 choices actually, about what we could apply at point P in order to make this not move at all, okay? In order so that it has a torque of 0, so it's not rotating at all, okay? So I'll let you make a decision on that. That one's pushing at the pivot point, yes. Yes, Kevin.
I have the answer.
If you push, that's kind of like pulling the door.
Because the
Pulling,
balance
if you go
we
Z,
just literally
that's
explained.
kind of, it's opposite of this. Both rotational don't need to be.
What do you think?
This is going to rotate this way, so we need a force that's going to rotate this way. So then we see.
Because this one is 0 because it's at the pivot.
Okay, so this one, that one, look.
Okay, I see what you're saying.
Oh, man.
All right. Somebody give me a wrong answer.
A.
A, okay. Oh, by the way, so this point, this vector right here, that we don't even worry about that because it is not exerting any torque. Why is it not exerting any torque? Because it's pushing right at the pivot, which means you have a radius of 0, not causing it to rotate at all. This vector right here, this force, is going to cause a torque in which direction? It's wanting to go that way. So we're going to need this to be working something to be able to fight it to go that way, okay? And make it go clockwise, okay? But why not A?
Because it's going to be too much to where it will actually move clockwise.
It's not moving.
It needs to be equal.
Okay, okay. So,
Oh, wait, oh no. The answer's A.
That's like.
the answer is A.
Yeah, because it has to be greater because the radius is less than the radius of the other one.
That is correct. Yeah. See, the thing is that this one's farther away, so it doesn't need a hole. So it's pushing, at a distance of maybe 10.
Oh, because it's closer. Oh.
This one's closer, okay? Distance of 5, so it's going to have to be more. Okay. All right, and point the other way. That's why D is not, or C is not correct. D, I saw a lot of people putting D. Notice D would actually be along the line of the pivot. That would give you equilibrium along a line, sort of like it's not going to be moving back and forth, but we're talking about rotational at this point. Okay, so D, that's not D. What's E going to do?
Oh, it's gonna help you go faster.
Yeah, it's going to work together. All right. That's correct. Okay. Let's very quickly talk about center of gravity. Get us started on tomorrow's. We're gonna do a little bit of center of gravity today and a little bit tomorrow. Okay, so gravitational torque and the center of gravity. So if you haven't taken notes on 7.4, take notes on 7.4 and on 7.5, because 7.4 is actually pretty short. Whatever we don't cover in the next 5 minutes, we'll wrap up on 7.4 tomorrow. Okay? All right. So we have a gymnast here. We've just said that we have anytime you have a force acting at a distance on something, then it's going to cause that thing to rotate. All right? Well, in this case, we have a person, and if we think of this as the pivot point, all right, well, she's just not one point. She is made up of bones and muscle, and what's pulling down on all of that bones and muscle?
Gravity.
Gravity. In fact, the bones and the muscle and her hair and her skin, all that, that's all made up of, you know, different molecules and things like that, proton, and then smallest level you get the protons and neutrons and electrons and the subatomic particles and things like that, and all of those are being pulled down by the Earth's gravity, right? So, and if they're also all kind of connected, okay, if you kind of think of her like this this meter stick, then you have on the particle that's right here, it's being pulled down, so that very small electron right here is going to be exerting a torque on her hands, okay? And then there's an electron over here, which is also being pulled down. Actually, there's billions upon billions of electrons and protons right here, and they're being pulled down by gravity. Same thing right here. And even all the way down to her feet, there's protons, electrons, and they're all being pulled down by gravity, and so they're going to be exerting a torque. Does that make sense? So when we start dealing with actual things, and we talk about if they're in a gravity field, like if they're on the Earth, okay, then there's going to be torque exerted on the pivot point based on the gravitational force, okay? So what we do, you know, we could sit around forever and ever and ever and say, all right, what is the distance that her feet molecules are from the pivot point, and let's multiply, you know, figure out what that force is based on the weight due to gravity, force of weight due to gravity, and at that distance, and for her calves, and all the way up here, figure out each one of those, okay, and add them up, billions upon billions, right? That would take forever to figure out what's the torque caused by gravity here, and here, and here, and here, and here, and here, and here. So instead, what we do is we sort of condense all of those points, okay, and we treat every object here in physics as if all of the mass is located at one particular point. We have different mathematical tools that we can do that, but that one particular point is what we call the center of gravity, okay? And then so what we would say is that the center of gravity is where we're going to draw the weight force, okay? And so in this case, we can model what's going on here with our gymnast by saying there's a gravitational pull on her right there at the center of gravity, which is this distance from the pivot point. And then we can do our calculations. So we can say there is a torque on the pole here at this distance and with that force, and then we could also calculate the angle as well. All right? So tomorrow what we're going to talk about is how that deals with balance, okay? And some other ways of finding out the center of gravity. So if you haven't read about that, read about that, take the notes. I'm checking all 3 notes tomorrow, 7, 3, 7, 4, 7, 5. Today we talked about torque, a little bit about center of gravity, and about the things that make the torque effective.